Hello everyone. So in this video we will continue our discussion about the photochemistry. If you remember, we have discussed a lot of things about this photochemistry and photochemical reactions. In our previous video we have talked about how to predict the mechanism for a particular reaction and what are the factors that we need to look at when we try to interpret a mechanism. We have identified 4 factors which we need to be concerned of. First thing is the thermodynamic aspect of the particular reaction, or we can call it simply energetics. And then we have talked about the dynamic aspect of the reaction. And now in this video we are going to focus around the structure, and finally there's a effect from the electronics. Now these two, energetics and the dynamics, we have discussed about it. So if you want to look at about these factors, if you want to understand how these factors are going to affect our mechanism, I highly recommend you to watch this video. I'm going to put the link here. Now today in this video, let's talk about the structure, right? We are going to talk about the structure. Now when it comes to the structure, let's start our discussion with the chromophore. We have introduced this term called chromophore in our last video. Now when it comes to the general photochemical reactions, we can identify 2 main chromophores, right? This is the first chromophore, which is more common, and there's another chromophore like this one. So this is basically the oxygen, right? This is the oxygen, and this is the carbon-carbon chromophore. Here, carbon-oxygen chromophore. Okay. Now let's talk about this each structure, each differences, how these are going to be affect our particular mechanism. First, let's go to the carbon-oxygen one. This is the carbonyl group. When we talk about the carbonyl groups, right, the chromophore is the lone pair. The lone pair on the oxygen. This is the chromophore, right? So our energy, our light is going to be absorbed by these electrons. Now what happens is this one. We have the pi orbital. Now I'm going to just sketch the molecular orbital diagram for this particular structure, right? So there's a pi electrons, which is this pi bond. This pi bond, there are 2 electrons on the pi orbital, and there is also a sigma bond. I will not draw the sigma bond on this case, right? There's a sigma bond also in this diagram, right? So I'm not going to draw the sigma bond because the sigma bonds are not going to be affected by the photolysis. They are not going to be excited, so we can forget about the sigma bonds. Let's focus about this pi bond, and then there's the lone pair. This is the N representing this lone pair. There are 2 electrons on the lone pair. Now here we have the pi star, right, which is the excited state, like the antibonding orbital of the pi orbital, right? Now when the light or photons have the contact with our chromophore, what happens is these lone pairs, one of the electrons in the lone pair will absorb the energy and they will get excited. Now this electron will go into the excited state, resulting this kind of molecular orbital diagram. Now here we have 2 electrons on the pi orbital, which is not changed. Now in the lone pair, like in this lone pair, right, this is the bonding orbital, right? I hope I will mention this for simplicity. This is the bonding orbital. This is the anti-bonding orbital, and this is the non-bonding orbital. which is represented to the lone pair on the oxygen. Now the non-bonding orbitals is going to absorb the energy and go into the higher energy states. So here in this case you only have one electron. What happens to the other electron? It has excited. Okay, it has excited. Now this is our singlet excited state. Singlet excited state. Okay, so this is S0, this is S1. This is the singlet excited state. Now if I ask you what is the transition, what's the transition in this excitation process? Now you can see our transitions occurs through non-bonding orbital to the anti-bonding orbital. So we call this transition as N to pi star transition. N to pi star transition. Okay. Now this is the singlet excited state. If you remember, after the formation of the singlet excited state, there is another possibility. Let me take another color, which is the intersystem crossing. The intersystem crossing can happen. What happens now? Here we have the same orbitals. Nothing is changed here. The only change is the spin. The spin is going to be changed. Now this is called the triplet excited state. We have talked about this triplet excited state formation in our first few videos, right? I hope you remember. Now there's a reason why the direct transition from ground state to the triplet excited state is not happening, right? This is not possible. Why? It's because of it's not allowed. We have talked about it. Only thing is possible is this intersystem crossing. After that it can come into the ground state. This transition is not possible. So this is the process for this particular chromophore, like N to pi star transition. Now if we consider a pi bond with carbon, let's take this example. Okay, and here we have the carbon bond. Now you can see there are no lone pairs, right? So there's a sigma bond here and there's a pi bond here. So we can draw the sigma bonds and the pi bonds. Since the sigma bonds are not involving in the photolysis, otherwise the excitation process, I will delete the sigma bond. Now in the pi bond there's 2 electrons. I will draw the pi star, which is the antibonding orbital too. Now what happens is when the energy is being absorbed, 1 electron will be going to the high energy states. Here the excitation process will happen. Here we have the higher energy electron. Okay, so this is the singlet excited state. Which is denoted as S1. This is the S0, singlet ground state. Okay. Now there's the possibility of the intersystem crossing. The same thing. Nothing is different. Only the spin is changing. Now this is called the triplet excited state. Right? This is called the triplet excited state. Now let's compare these two. Now what happens through this excitation? What's the purpose of this excitation, right? If you look closely about this particular bond here, right? If I ask you to calculate the bond order in the ground state, this S0 ground state, and the excited state, there could be 2 results. In the ground state, you can see the antibonding orbital is empty, right? The antibonding orbital is empty. So if I calculate the bond order, how to calculate the bond order? The bonding electrons, 2 electrons is there, minus the antibonding orbitals is 0, 2 equals 1. Now in the excited state, right? In the excited state, you will see there's a electron on the antibonding orbital. So there's a reduction in this case. This is not 0 now, this is 1. So you can see the bond order is now decreasing. In this excited state, we have lower bond order compared to the ground state. Now, what is this bond order means? Bond order means the energy, like otherwise the stability of your bond. So in this case, when we look at this carbon oxygen bond, the decreasing of this bond order means that our bond is going to be weak. Since the occupation of this antibonding orbital towards the pi star is the antibonding orbital of the pi star, our pi bond over here going to be little bit weakened. Now in the excited state, our molecule would be much more like this. Our pi bond is halfly broken, right? Because now there's this occupation of the antibonding orbital. Since this electron is on antibonding orbital, we have this weakened pi bond. With the reaction, what can happen? This bond is broken. Sorry, this bond is weakened. So there can be radical formation like this. Okay, the radical can be formed. So let me draw it here. Now what happens? Here we have the initial. This is our initial molecule. Now when the excitation happens, you know this bond is going to be weakened. Now this bond is weakened. Now if we introduce a radical to our reaction mixture, this can easily undergo radical reaction mechanism. There's a radical here. If we introduce a radical to here, to this particular position, a reaction would be much more less feasible. Why? Because this bond is much more stronger. This is on the ground state. This is ground state. It's not ground state. This is the excited state. This is the excited state, which is S1 or T1. Now in the ground state, you know the bond is much more strengthened, right? The bond order is high. So bond is not weakened. This bond is strong. So our radical cannot interfere towards this bond and create go through the reaction. It can't do it because this bond can't be broken easily. Now in this case, in the excited state, we have an electron in the antibonding orbital which decrease the bond order. Now this bond is weakened. Now our radical can easily involve in the reaction. This is the case how the structure affects our reaction. Now when we look at this carbon-carbon case, right, the same thing happen. You can see the antibonding orbital here, pi star is occupied. So bond order is going to be decreased. Now what happens? This has weak pi orbital between the carbons. So if we introduce a radical substance to our mixture, this bond can easily be broken from this to proceed with the reaction. So we have the results like this. Here we have the result. A radical is being formed. So this is the reactive intermediate. If you remember our previous video, we have talked about this reaction procedure. And this is the reactive intermediates, which is essential for photochemical reaction. In this case, this is the reactive intermediate, right? I hope it's okay with you, right? I hope you got